Section 2.2, complements and subsets. In this section, we will discuss complements and subsets. Let's go to our notes to begin, and we can see some definitions. Section 2.2 notes. First thing we're going to define is called the universal set. The universal set is defined as the set of all elements that are being considered for that particular problem, denoted by the letter U. So when we talk about a universal set, we mean those are the only elements in the world as far as this particular problem is concerned. That will make more sense as we continue and look at our examples. Second definition is the complement of set A. The complement of set A is denoted by the letter A with an apostrophe next to it, and it is the set of all elements of the universal set that are not elements of A. The complement of set A is the set of all elements of the universal set that are not elements of A. It's basically like the opposite of set A, if you want to think of it like that. Next definition I want to highlight is the subset of a set. Set A is a subset of set B, and we denote it by this notation right here, if and only if every element of A is also an element of B. So when we use this notation right here, we're saying A is a subset of B, and what we mean is that every element in A, which is on the left side, also shows up in B, which is on the right side. The next definition is proper subset. Set A is a proper subset of set B. And notice the slightly different notation. See these two notations compared to each other? This one has the little line under it. This one down here does not. When we don't have the little line under it, we call it a proper subset. This says A is a proper subset of B. So A is a proper subset of B if every element of A is also an element of B, but A is not equal to B. Every element of A is also an element of B, but also A cannot be equal to B. So if we're going to call something a proper subset, they are not allowed to be equal to each other. If we are just going to call something a subset, like up here, they might be equal to each other. They're usually not, to be honest. Usually when we say subset, we don't mean them being equal to each other, but they could be. If we say subset, these two things could be exactly the same thing. But when we say proper subset like this, they're not allowed to be equal, but also every element of A has to show up in B. I want to highlight this definition right here. It says the number of subsets of a set within elements has 2 to the power of n subsets. A set within elements has 2 to the power of n subsets. And then the next one says a set within elements has 2 to the power of n minus 1 proper subsets. The minus 1 comes from the fact that we have to remove the one that's equal to the original set. I know that probably doesn't make a lot of sense right now. It hopefully will make sense when we start looking at the examples in a few minutes. Last thing I want to highlight here is something I think we've seen before, Pascal's triangle. And I just want to highlight this because it's going to pop up a little bit today. Pascal's triangle is something I showed you guys a few sections back. And I said, it's just something that pops up in math at random places. And today's going to be one of those. Okay. So for our first example, it says, let the universal set U equal 0, 2, 4, 6, 8, 10, 12, 14. Anytime we use the letter U, that automatically means universal set. I don't even really have to say it, but I am for, at least for today, I'll probably say, hey, that's the universal set. But in general, when we use the letter U, that means universal set automatically. Find the complement of each given set. Remember, the complement is denoted by A with an apostrophe right there. Okay, so this is set A, this is A complement. Set A complement. So remember what the word complement means here. It means we're about to say a bunch of nice things about set A. Actually, it does not. The definition of complement is actually the set of all elements of the universal set U that are not elements of A. A complement basically means the opposite of set A. That was a joke, if you missed it, about saying nice things about set A. Did you guys know there are 3 different types of math teachers? There are those who can't count and those who tell bad jokes. Okay, back to this problem. A complement, remember, means basically the opposite of set A. Means everything that's not in set A when we compare it with the universal set. Let me say that again. This is read as A complement. That is everything that's not in set A when compared to the universal set. So what is in A complement? Well, basically everything you don't see here, but you do see it up here. So we got 0, 2, 4, 6, 8, 10. We got 0, 2, 4, 6, 8, 10. But up here I have 12 and 14. I don't see 12 and 14 down here, right? 12 and 14 would be in what we call A complement. And that's really it. It's the opposite of set A. It's everything that's not in set A when compared with the universal set. So A along with A complement has to make up the entire universal set. Let's do the same thing for part B. Let's find B complement. Remember, B complement is a set, and it's the set of all elements that are not in set B. B complement is the set of all elements that are not in set B when compared to the universal set. You have to have a universal set. If we're going to ask about complements, there must be a universal set defined. So let's talk about everything that's not in set B. Well, 0 is not in set B, so 0 is going to be in B complement. 2 is in set B, but 4 is not in set B, so 4 is going to be in B complement, right? 6 is right there, but 8 is not. 10 is right there, but 12 is not. And then finally 14 is right there. So that's what we call B complement. Notice that B along with B complement should have all of the elements in the universal set. The next couple questions are a little different because the set that we're trying to find the complement of is given as a word description. This says that set C equals the set of even natural numbers less than 10. We're supposed to find the complement of set C. I think in a case like these last couple, it's a better idea to actually figure out what does set C look like first. And after we figure out what set C looks like, then we can start talking about the complement. So I think we should do something in the beginning before we even find C complement. I think we should define what set C looks like, and then we can start talking about C complement. Set C is the set of even natural numbers less than 10. If you remember from a previous section, the natural numbers are 1, 2, 3, 4, 5, 6, 7, 8, and so on. They don't include 0. So if we're talking about even natural numbers, we're talking about 2, and we're talking about 4, and 6, and so on. But we want only the ones that are less than 10. So I want to include 8, but I want to stop right there because those are the only even natural numbers that are less than 10, right? Those are even numbers. Natural means I'm not including 0. And those are the ones that are less than 10. That's not my final answer. That's just a roster method description of set C. This is a word description of set C. These two things are saying exactly the same thing. We haven't even done anything yet. We need to find the complement of this set. But I think it's a good idea to turn the word description into the roster method description before you try to find the complement. So once we have set C now we can talk about the opposite of set C, the complement of set C. So now I'm going to list everything that's not in set C when I compare it to the universal set. So for example, 0 is not in set C. So 0 would be in set C complement. 2 and 4 and 6 and 8, they are in set C. 2, 4, 6, 8. They are in set C. So they're not going to be over here, but 10, 12, and 14 will be over here. So my final answer is this. My final answer is not this over here because this is I haven't even done any work yet. This is exactly what the original question said. I just stated it in a different way using the roster method. This is C complement over here. Let's do part D. D says it's defined as the set of even prime numbers. We ultimately want to find D complement, but I think we should just figure out what set D looks like first before we start talking about the complement of it. I know set D is defined as a word description here, but what does set D look like using the roster method? I actually think we should probably remind ourselves what a prime number is. A prime number is a number greater than 1 with no divisors other than 1 in itself. Prime number is a natural number greater than 1 with no divisors other than 1 in itself. So when we talk about prime numbers, we're starting bigger than 1 anyway. So like considering 2, 3, 4, 5, 6, 7, 8, and so on. And those are candidates for prime numbers. But the only ones that are actually prime numbers are ones that have no divisors other than 1 in itself. It means they're not divisible by anything except for 1 in itself. I have a list here of all the prime numbers less than 1,000. These are all the prime numbers less than 1,000. 2 is a prime number, 3 is a prime number, 5 and 7 and 11 and 13. Those are prime numbers. Notice that 2 is the only even prime numbers. All of the rest of the prime numbers are odd. That doesn't mean that all the odd numbers are prime, but all the prime numbers are odd except for 2. Why is 2 the only even prime? Well, because any even number bigger than 2, like 4 or 6 or 8 or 10 or 12, they're automatically divisible by 2. But remember, the definition of prime is that you can't have any divisors but beside one in itself. You can't be divisible by anything except one in itself if we're going to call you prime. So 2 is going to be the only even prime number. Let's take like 13, for example. Why is 13 prime? If I tried to divide 13 by anything, it's not going to work out well for me. It's not going to work out perfectly for me. Try to do 13 divided by 2. It's not going to go well. It's not going to go perfectly. You're going to have a remainder or you're going to have a decimal answer. Try to go 13 divided by 3. It's not going to go well. You're going to have a remainder or a decimal answer. Try to do 13 divided by 4. You're going to have a remainder or a decimal answer. It's not going to go perfectly, right? The only things you can divide 13 by and make it work out nicely is 1 and 13, 1 in itself, right? That's what we mean by this definition here. Has no divisors other than 1 in itself. So what I was saying was, I think I said 13 divided by 2. Well, it doesn't work out perfectly. We have a decimal answer, right? 13 divided by 3. It doesn't work out perfectly. We have a decimal answer. And so on. 13 divided by 4. It's not going to work well for anything except, of course, if you go 13 divided by 1, I mean, everything divided by 1 works out nicely, and everything divided by itself works out nicely, right? With no decimal answer. But if you take 13 and divide it by anything else, it's not going to go nicely. It's going to have a decimal answer or what you might call a remainder. And that's what makes 13 prime. So if that D is described as the set of even prime numbers, you might remember just a minute ago, I said 2 is the only one. I said 2 is the only even prime number on this list. All the rest of the prime numbers you're going to notice are odd. So 2 is the only even prime number. So when we talk about set D being the set of even prime numbers, well, ultimately I want D prime, but I think I'm getting a little ahead of myself because I think first I should define set D, which just consists of the number 2. So again, ultimately I want D complement. I think I might have said D prime a minute ago. That's it's another verbiage that we use sometimes in other math classes, but in this class we should say D complement right here. Okay? D complement is the opposite of D. D complement means everything that's not in set D when compared with the universal set. So first thing I think we should do is define set D, which I did right here. 2 is the only even prime number. And once we've defined set D, we can start talking about the opposite of set D. So the opposite of set D is going to be everything up here except for 2, right? It's going to be 0. And it's not going to be 2. And it's going to be 4. And it's going to be 6 and 8 and so on. So this is my final answer. That is D complement. This is just another way to say D, right? D was given as with a word description as the set of even prime numbers. That just translates into roster method as D equals the set consisting of the element 2. I haven't even done any work yet here. This down here on the bottom left is saying exactly the same as what we were given, just in a different form. The work comes when I take the opposite of set D and I turn it into D complement. Okay, next page. Consider the following sets. Set U consists of, now these are people this time. These are not numbers. These are people. Abe, Ben, Cal, Dex, Eva, Faye, Gil, Hal, Ian, Jax. That's set U. I'm reminding you that that's the universal set, although I didn't need to. As soon as we use the letter U to name a set, that's automatically the universal set. I guess I was just in a good mood by reminding you of this. Now, these other sets are defined this way. Set S has Abe, Ben, Cal, Dex, and Jax in it, and so on. So I define the universal set, and then I define 4 other sets. We are going to determine whether each statement is true or false. Use the camera a little bit so we can see the whole page. Okay. As always, I encourage you while you're watching these videos to pause at moments like this and go try to say true or false on your own before we start talking about it together. I don't think it's a good idea to always just watch me do the problem. I think you need to try the problem and then come back and we can look at it together. So I'm going to keep going here, but you should pause right now and work these problems out, and then you can unpause and see how they go. Part A says Z is a subset of T. Z is a subset of T. Do we think that's true or do we think that's false? To remind ourselves what subset means. Here was the definition of subset right here. Set A is a subset of set B, and we denote it by this notation right here. A is a subset of B if and only if every element of A is also an element of B. Be technical, I should probably have if and only if right here also. But back to that. Set A is a subset of set B, denoted by A is a subset of B, if and only if every element of A is also an element of B. That means that everything that shows up on the left-hand set also has to show up in the right-hand set. Everything that shows up in set A also has to show up in set B. That's what that means, right? So if we're going to say true on this one, then everything in set Z also has to show up in set T. Well, set Z consists of Cal and Gil. Really, it's just a question of, do you see Cal and Gil up here in set T? Because if you do, then we're going to say true. If you don't, we're going to say false. That's it. It's as simple as that. Set Z consists of Cal and Gil. Do you see Cal in set T? Well, I do. Do you see Gil in set T? I do. So Cal and Gil both show up in set T. So everything in set Z is also in this one. That's why we're saying it's true. Z is a subset of set T. Again, everything here also shows up over here. But look at part B. Z is a subset of S, true or false? Does everything in Z also show up in S? So now we're comparing Z with S. So everything in Z also show up in S. Well, Cal does. I see Cal in set S right there. Do you see Gil in set S? No. Gil is causing a problem here. Gil is in set Z, but Gil is not over here in set S. So it's not true that everything in set Z is also showing up in set S. This is a false statement. And it's really Gil that's messing this up. Gil is the issue. Gil is the reason we are saying false. Next question. Is S equal to T? You may remember that definition from a previous section. For two sets to be equal to each other, they must look exactly the same. Do sets S and T look exactly the same? You can quickly see the answer is no. I mean, set S has Abe in it. Set T does not. We can say false already. Set S and T are not equal to each other. They do not look exactly the same. We can say false on this one pretty quick. Again, this definition, that's not from today. That was from a previous section. Also, this definition is not from today. This was from a previous section. This is equivalent to. Remember, when we say equivalent to, we just mean they have to have the same number of elements inside of them. They don't necessarily have to be the exact same elements as each other, but they just have to have the same amount of elements as each other. They have to have the same cardinality. That's a word we used in a previous section. If S and T have the same cardinality, we can say true here. If not, we need to say false. How many people live in set S? 1, 2, 3, 4, 5. How many people live in set T? 1, 2, 3, 4, 5. They have the same amount of elements, so they are equivalent to each other. So this is true. Notation we used in a previous section was the number of elements in set S was equal to the number of elements in set T. Or we could say the cardinality of set S equals the cardinality of set T. They both happen to be 5 in this case. But as long as the number of elements in each set are the same, we can say that two sets are equivalent to each other. That is a true statement here. They're not equal to each other, but they are equivalent to each other. For the next example, or the next part, part E, I think it's talking about W complement. I think we should figure out what is W complement before we start trying to figure out if it's a subset of S. Let's just go see, what does W complement even mean? W complement means everything that's not in W. Remember, when compared to the universal set. So Abe is not in W. Ben is not in W. Hal is not in W. But Dex is. But Eva is not in W. But Faye is, and Gil is, and Hal and Ian and Jax are. So I think W complement would just be this set right here. Again, if W is defined like this, W complement would be the opposite of set W when compared with the universal set. Means everyone that's not in W, but they are in the universal set. Those are these people right here. Now we're trying to figure out, is that a subset of set S? Let me just copy down what set S is. That's Abe, Ben, Hal. Let me see if I could squeeze here. Dex, Jax. I just copied set S. So everything in the left-hand set also showing up over here. Almost, but no. Almost, but no. This is false because Eva shows up in W complement, but Eva does not show up in set S. This is a false statement. And it's Eva that is causing us to say false. Eva's the problem. Eva is showing up in W complement. Eva is not showing up in the right-hand set, which is S. Therefore, W complement is not actually a subset of S. That is a false statement. Last part of this question says the number of elements in Z complement is greater than the number of elements in W. Or the cardinality of Z complement is bigger than the cardinality of W. So now we're talking about how many people live in Z complement and how many people live in W. And is the one on the left bigger than the one on the right? How many people do live in Z complement? I guess I could go figure out Z complement, but I don't think we need to. There's only two people that live in set Z. So how many people don't live in set Z? Remember, when we do that, we're always comparing with the universal set here. I think we should just count how many people live in the universal set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The universal set has 10 people in it, right? 10 people live in the universal set and 2 people live in Z. 10 minus 2 is 8. I hope you guys are okay with me saying that 8 people are in Z complement. 10 minus 2. Let me say that again. 10 people live in set U, which is called the universal set. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The number of elements in the universal set is 10. We can see the number of elements in Z is just 2, those 2. So that means the number of elements not in Z when compared to this would be the other 8, right? If Cal and Gil are the only ones in Z, then the rest of the 8 are not. That's the 8 down here. That's the number of elements that are not in Z. I hope that makes sense. Number of elements in W, 1, 2, 3, 4, 5, 6. Number of elements in W, 1, 2, 3, 4, 5, 6. Is 8 bigger than 6? Yes, it is. This is a true statement. Moving on to our next example. We are given a set here and we are being asked to find all of its subsets. We are given a set and we are asked to find all of its subsets. More. We are given a set and we are asked to find all of its subsets. Reminding ourselves the definition of subset. A is a subset of B if and only if every element of A is also showing up in B. But how many subsets does a set have? Look at this right here. A set with n elements has 2 to the power of n subsets. It's going to be important right here. A set with n elements has 2 to the power of n subsets. The problem we are looking at right now has 3 elements, 1, 2, 3. If I will go ahead and put a 3 right there, 2 to the third power, that means 2 times 2 times 2, that means 8. That means I expect 8 answers down here. If I'm trying to list all the subsets, I expect 8 of them. That means a set with 3 elements needs to have 8 subsets. That's kind of like nice because that tells me how many answers I'm looking for down here. I'm looking for 8 answers. So what are those 8 answers going to be? Well, for example, here is a set, and that's one of my 8 answers. It's not a very big set, it just has one element in it, but every element in this also shows up in the original. So this is a subset of that. And obviously, now that you see that, I can say, well, here's another one. That's another subset of the original. Here's another one. So far I have 3 of the 8. We know there's going to be 8 because 2 to the power of 3 equals 8. There's 3 elements. Here's the formula for number of subsets. 2 times 2 times 2 equals 8. I need some more though. Well, sometimes we can talk about a set with 2 elements in it. Like, for example, this set. This set has cardinality 2, but this set is also a subset of the original. Right? Everything that shows up in this set also shows up here. So here's another subset of that one. But here's another one, A comma C. That is a subset of the original because everything that shows up here also shows up here. And then also B comma C would be a subset of the original because B and C are both in here. So we got 6 of the 8. We know there's 8. So there's 2 more that we're missing. Now, sometimes I see people write like B comma A. That's not any different than this one up here. Just because you change the order does not make it a different set. So we're not going to talk about B comma A. We're not going to talk about C comma A. No. What we are going to talk about though is this set with 3 elements. And you might say, oh, come on, that's not a subset. That's just equal to the original. I know it's not what you might think of as a subset, but it does meet the definition because the definition just says, is everything in this one also in this one? Is everything here also in the original? And the answer is yes. And you say, well, that's a cheap answer. Well, I know it is, but it's still an answer. The entire thing is considered a subset of itself. That's kind of weird, but it is. It's not a proper subset. Remember, that was a different definition. This is not considered a proper subset of this, but it is considered a subset. But we're only at 7 of them now. We needed 8. We know we needed 8. It says it right there. So we're missing one. Which one are we missing? This one's also kind of a cheap answer. Remember the empty set? The empty set is the set that has nothing in it. It's literally empty. Does everything here also show up here? Well, I guess so, because there's nothing here anyways. There's nothing to even check, right? The empty set doesn't even have any elements in it. So I guess technically the empty set is a subset of the original. In fact, the empty set is going to always be a subset of the original. The empty set and the set itself are always going to be subsets of the original. Those are the cheap answers. The other ones are the ones we got to think about a little bit, but the ones that people forget sometimes are the empty set and then the entire set itself. They are also considered to be subsets. So these are the 8 that we are talking about right here. Those are the 8 that we are talking about. I knew there was going to be 8 answers because of that formula. This is the formula for number of subsets of a given set. There's 3 elements, 1, 2, 3. We stick a 3 right there. 2 to the third power equals 8. I want to point out something also interesting before we move to the next example. Notice that there is one element, or I'm sorry, there was one set with 0 elements. There were 3 answers with 1 element each. There were 3 answers with 2 elements each, and there was 1 answer that had 3 elements. See how I kind of organized them? This had nothing. These all had 1, these all had 2, and this one had 3. But look at this right here. Happens to also be one of the rows of Pascal's triangle. Let me show you that again. One, three, three, one happens to also be one of the rows of Pascal's triangle. I'm going to try to calm down right now. I am super excited. I have goosebumps right now. I know you probably do also. Let's try to bring the excitement level down a little bit, and we'll move on to the next problem. Pascal's triangle shows up in some crazy places in mathematics. There is a restaurant in Davis called the Hot Dogger. They only serve hot dogs, and they offer 4 different condiments that you can put on your hot dog. They offer ketchup, mustard, relish, and sauerkraut. I used C for condiments, right? So that's the set of all the condiments that they offer. They offer 4 condiments. You can order a hot dog and then they ask you, what do you want on it? But these are your choices: ketchup, mustard, relish, sauerkraut. How many different types of hot dogs could you order? How many different types of hot dogs could you order with 4 condiment options? That's the question. How many different hot dog condiment combinations are possible? For example, I could order a hot dog with ketchup and mustard. I say, give me a hot dog. I only want ketchup and mustard on it. That's one type of hot dog I could order. But how many like that could I order? How many different hot dog condiment combinations are possible? You might not realize it, but I'm asking you how many subsets of set C exist. Think about that. For example, I said I might order a hot dog with just ketchup and mustard. That's ketchup and mustard. That's a subset of set C. How many different subsets of set C are there? That's what we're being asked right here. How many different subsets of set C are there? Notice that set C has 1, 2, 3, 4 elements in it. Notice that the cardinality of set C equals 4. The number of elements in set C equals 4. Remember that formula I just showed you, that if you're trying to figure out how many subsets are there of a given set, you take the cardinality and you put it right there for n. So I'm expecting 2 to the power of 4. That means 2 times 2 times 2 times 2. That means 16. I'm expecting there to be 16 different hot dog condiment combinations. I'm expecting there to be 16 different sort of types of hot dogs you could order at this restaurant as far as what condiments are going to go on your hot dog. Because there are 16 subsets of set C, because set C has 4 elements and 2 to the power of 4 equals 16. But what are they? That's what the next question is asking. What are all of the subsets? This part A was just saying how many are there? Part B is saying, tell me what they are. Tell me all the different types of hot dogs you could order. I know there's 16 answers, but show me all 16. That's what we're being asked down here. So this is very similar to the last example where we knew there was 8 answers, but we needed to show them, right? What I think is a good idea for you to do right now is pause this video and go try to find all 16 of them. I think it's a good idea to do it in a some sort of a orderly fashion. Like show all of them that have 1 condiment each. Show all of the subsets that have 2 condiments each. Maybe try to show all the subsets then that have 3 condiments each. I think if you just randomly go about this, you're either going to repeat some or you're going to miss some. I think you should pause this video and try to find all 16 and then unpause and come back and see how you did. So I'm going to start with probably, the easier ones. Like, for example, you could definitely order a hot dog with ketchup only. I'm just going to abbreviate here. You can definitely order a hot dog with ketchup only. That is one subset of set C. You could definitely order a hot dog with mustard only or relish only or sauerkraut only. There are 4 types of hot dogs you could order that have exactly 1 condiment on it. So we got 4. We need a lot more. We got to have 16 total, but we have 4 so far, right? Those are 4 hot dogs that we could order. But I think I mentioned I could order something with ketchup and mustard. That's a hot dog. That's another answer. Ketchup and mustard only. How about ketchup and relish only? How about ketchup and sauerkraut only? Right? So now see what I'm doing? I'm trying to list all of them that have exactly 2 elements each that are subsets of this given set C. How about mustard and relish only? That's another kind of hot dog I could order, just mustard and relish. How about just mustard and sauerkraut? How about just relish and sauerkraut? Can you come up with any more that have exactly 2? I don't think you can. You can try, but I think you're just going to repeat one of these. Again, remember, if you just switch the order, that doesn't make a new set. If you put, for example, M comma K, that's not any different than this one here, K comma M. Just switching the order of the elements in a set does not make it a new set. So I think we've exhausted all of the subsets with 2 elements each. How about 3? Well, I could do ketchup, mustard, and relish and tell them I don't want sauerkraut. Say, give me everything except sauerkraut. That's another type of hot dog, right? I could do ketchup, mustard, and sauerkraut and say, no relish, please. Hold the relish. I could do ketchup, relish, and sauerkraut and say, no mustard, please. And finally, I could say, hold the ketchup, right? So mustard, relish, and sauerkraut only. So I think those are the only ones. There's four of them right there, but I think those are the four subsets of set C that have three elements each. It should make sense that there are four of them because it kind of you know, matches up with the four over here in a way. Because like on the first one, I was holding the sauerkraut. On the second one, I was holding the relish. On the third one, I was holding the mustard. On the last one, I was holding the ketchup. There should be four of them because it's just which one are you going to leave out, right? That's it. So what do I have? I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. We're close to 16. We're almost done, but we need two more. I got 14 answers so far. I know there should be 16. What are the other two? These last two are the ones that people forget about sometimes because people forget that the entire original set is actually also considered a subset of itself. It's not a proper subset of itself, but it is a subset of itself. You could certainly order a hot dog and say, give me everything. Give me the works. I want ketchup, mustard, relish, and sauerkraut on it. I want everything on it. That is technically considered a subset of itself because everything in this one also shows up in the original. So now we're at 15. Remember that last one that I said some people forget about this one? That's the empty set. This is where you say, give me a hot dog plain. I want nothing on it. Plain hot dog. See all the condiments? There's nothing there. There's no ketchup, no mustard, no relish, no sauerkraut. This is the empty set. This represents a plain hot dog with no condiments at all. But that is a different type of hot dog you could order. That's one of the 16 that we could order. Now we have all 16. This is my answer. Those are all 16 different types of hot dogs we could order at this restaurant. You ready to be blown away again? There is one subset with zero elements. There are four subsets with one element. There are six in this column with two elements each. There are four in this column with three elements each, and there's one over here. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. Pascal's triangle shows up in some crazy random places in mathematics. This is a little bit eerie. This is like scary movie type of stuff. Some of you want to run and hide right now. Pascal's triangle just randomly shows up in some crazy places in mathematics. 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. We're going to move on to our last example. There is a restaurant in Elk Grove called Original Pete's Pizza. They only serve pizza and they offer 12 different toppings to choose from. How many different pizza topping combinations are possible? This is very similar to the problem we just did. Very similar. Previous question talked about 4 toppings that you could put on a hot dog. And we figured out there were 2 to the power of 4 or 16 different types of hot dogs I could order. This one talks about pizza and we have 12 toppings we could choose from to put on our pizza. And we want to know how many different types of pizza we could order, how many different pizza topping combinations are possible. Remember that formula that talks about how many subsets? 2 to the power of n. In the previous question, it was 2 to the power of 4. This time it's 2 to the power of 12. There should be 2 to the power of 12 different types of pizzas that we could order as far as what toppings are going to come on them. 2 to the power of 12, that means 2 times 2 times 2 times 2 times 2, 12 times, 4,096. I think I mentioned this in an earlier lecture. On my particular calculator, this is the button I use to get into the power or the exponent. If you see a button like that on your calculator, that's probably what you're using also. But a lot of calculators have different buttons. So whatever calculator you have, you should Google your name of your calculator and then how do I do exponents? Something like that. And on YouTube, for example, there will be probably many videos that will show you how to do an exponent on your calculator. So you don't have to sit there and go 2 times 2 times 2 times 2 times 2 times 2, 12 times. So figure out how to do exponents on your calculator. I can't just tell you because I don't know what kind of calculator you have, and there's many different buttons that exist on different types of calculators. So you're gonna have to figure out how yours works, but Google and YouTube should be helpful there. How do I do powers or how do I do exponents? And tell them what kind of calculator you have. Part B says, what is the minimum number of toppings that must be offered if the restaurant wants to advertise that it offers more than 50 million topping combinations? Right now, they have 12. Pete has 12 toppings. I don't know what those 12 are, but he has 12 toppings, probably pepperoni and sausage and mushrooms and stuff like that, right? But he has 12 of them. Right now, he already can offer more than 4,000 different types of pizza. You can order 4,096 different types of pizza at this restaurant as far as what type of toppings are going to come on your pizza. But I always imagine this as poor Pete gets home after a rough day of work, just wants to relax. He just wants to sit on the couch for a little bit. But Mrs. Pete comes in and she's bugging him. She says, Pete, we got to do better. We can only offer 4,096 types of pizza. We got to do better. I want to be able to offer more than 50 million types of pizza. We need more toppings. And Pete says, honey, we already have 12. Isn't that enough? We can already offer over 4,000 types of pizza. She says, Pete, I want more than 50 million. Then Pete gives in. He says, okay, I'm going to figure this out. I'm going to figure this out, Mrs. Pete. I'm going to figure out how many topping combinations, how many toppings we need so that we can have more than 50 million topping combinations. We need more toppings. We need more than 12. We need somehow for 2 to the power of n to be more than 50 million. Pete says, I'm on it, Mrs. Pete. I'm tired, but I love you. I had a hard day of work. I got pizza dough dust all over my hands and my clothes and my apron. But I pledge my life to you. I'm going to go figure out what power of n on 2 does give an answer bigger than 50 million because that's how many we need. That's the minimum number of toppings that we need so that we can offer more than 50 million topping combinations. So it really comes down to solving this. What power of n, what's the smallest power of n? What's the smallest power of 2, I should say? What's the smallest value of n that's going to go on the power of 2 that would cause the answer to be bigger than 50 million? Now, there is a way to actually go through some sort of algebraic method and solve for this. I'm not going to really talk about that in this class. This is not really an algebra class. We do more guess and check in situations like this. If you are just super in love with algebra, if you have a bumper sticker on your car that says "I heart algebra," I'm going to go ahead and tell you that you could use logarithms to solve something like this. There's something called logs or logarithms in mathematics. When the thing you're trying to solve for is up in the exponent, you have to use what we call logarithms. That's how you would do it. We're not going to do that. We're going to guess and check. We're going to start plugging in different values of n until we get an answer that's more than 50 million. We're going to guess and check. I want you to do that. I want you to go on your calculator. Well, first of all, you know the answer is bigger than 12 because a power of 12 only gives 4,096. You know n is going to be bigger than 12. Is it going to be 13? Go look at 2 to the power of 13. Is that bigger than 50 million? No. Is it 14? Go look at 2 to the power of 14. That only gives 16,000 something different types of pizza. Is it 15? Go look at 2 to the 15. That only gives 32,000. I want my answer bigger than 50 million. So you should go through the guess and check right now. You should continue looking at powers of 2, putting different values here until you hit the first one that gives you an answer more than 50 million. You should pause the video right now and go figure that out. Find the first power of 2, the first value of n that gives an answer bigger than 50 million. And then come back and see how you did. I think you will find the answer is 26 toppings. 26 toppings is the minimum amount of toppings that's going to please Mrs. Pete. 26 toppings is the minimum amount of toppings that's going to give us more than 50 million types of pizza that we can offer at this pizza place. Because if you kept going with the powers of 2, I did up to 15, but if you did 16, 17, 18, 19, 20, and so on, you get close when you hit 2 to the power of 25. You're at about 33 million right now, but that's not more than 50 million. 2 to the 25 gets close, but 2 to the 26 puts you over the top. 2 to the 26th power is 67 million something. That is bigger than 50 million. 26 is the first power of 2 that gets you more than 50 million. It gets you over that number. 2 to the power of 26. 26 is the first power of 2 that's bigger than 50 million. So 26 is the minimum amount of toppings that we need to offer if we are going to be able to say we offer more than 50 million types of pizza. We only offer 12 right now. We got to come up with about 14 more to get to 26. I don't know what those 14 are going to be. We should make Mrs. Pete figure that out. She's the one who wanted all this. That is it for this section. Thank you for watching.